In today's ScreenFlow, we're going to review some basic data structures, including stacks, pictured here in Waipio Valley on the Big Island, queues, and lists. And we'll also mention briefly the dynamic set data type. Stacks, as you remember, follow the last in, first out principle, LIFO. And often we draw it like this. Say we have some element, push A on the stack, and then B on the stack, and then C on the stack. The one that was pushed most recently will come out when you pop it. This organization of information is very useful for things like goal sub-goal structure. You know, like if you want to build a house, first you have to pour the foundation, and then you have to make the frame, and when you're making the frame there might be some specific things you have to do, like make the walls, and then raise the walls, and then nail all the walls together, and so on. And so often problem solving like that involves the larger goal, and then sub-goals that have to be solved, and then they may have sub-goals as well, and so on. And so when you're working on goal 1.1, you might want to have put on your stack, well, our big goal is big G, and so let's first work on goal 1, and for that let's work on goal 1.1, and so on. And then when you're done with one of these goals, and then you say pop it off, then you can say, oh yeah, I was working on goal 1. And then when you're done with that, and then you move on, you say, oh, okay, now I'm going to push goal 2. And that might involve some other sub-goals to get pushed on the stack. Eventually, you remember you're working on goal 2. So that's a typical kind of goal structure. And it also follows the hierarchical structure of programs. You know, the main program might be like the overall goal, and then these are the subroutines, and then these are other subroutines they call their functions. And so the same stack structure is used to keep track of what procedures are currently active in an operating system. So let's look quickly here at the operations of a stack. Just paste it in here so we don't have to write all this. So for the operations, of course, well, we've got an object type of stack, so we can create instances of them. This is a Java interface version of a ADT specification. A very simple one. It could be elaborated. But the basic operations are pushing something on the stack, popping something from the stack. It's an error if the stack is empty, so we might want to ask whether the stack is empty, just to be sure we don't pop and cause an error. Same thing with top. Inspecting what's on the top of the stack would be an error if it's empty. And we might want to ask how many things are on the stack. So that's the ADT specified as a Java interface, and it can be implemented in different ways. And in my web notes, you can see some properties capturing the intuition of the last in, first out, as well as other properties such as the fact that you can't pop an empty stack, and so on. Okay, so next we're going to look at some implementations. A common implementation of stacks is to use an array. Let's say we have an array S, and you allocate as much memory as you think you're going to need for your stack. And you have a top pointer. If this is an object-oriented approach, it would be s.top. And that s.top would point to the index of the first item in the stack. So if you're using, say, one-based indexing, s.top being equal to 0 would mean an empty stack. And then if s.top is pointing to a given position, like say 1, then you expect that there is some element E in there being stored. And as you push things onto the stack, you just keep incrementing s.top to point to wherever you've pushed the next item, like this. Now I'm going to put something else there, and so on. Let's bring up the code for this and look at a quick example issue. So here's And here's some example code. If, as I said, if the top is 0, then it's empty, otherwise it's not empty. Pushing means incrementing the top, as I just did here, and then assigning the object that you want to store in the stack to that position. And then popping, if the stack is empty, that might be an error. You might write out, in Java it's better to write out specialized exceptions that tell the user or other code more specific information about what went wrong, so those errors can be caught and handled. Otherwise, you decrement top and return the thing in the position that you just decremented. So let's take a look at a continuing example here. I'm going to maybe push a few more numbers on here, and I think I'll just do this all in blue so I don't have to keep switching colors. So let's say now s.top, well, it's currently 2 because that's where we got the last thing we put. So if we want to push something else, we increment it to 3, and we store, let's say we're putting the number 7 in here. And then if we want to store another one, we're going to increment it again, and to 4. I better write out my numbers here. And let's say we put some very large object here, like a big image or a movie. Okay. Now let's do a pop. So if it's not empty, so let's decrement top. Top is top minus 1, so top is now going to be 3, and then we're going to return top plus s of top plus 1. So top plus 1 is 4, so this will return VLO, very large object. And then let's say our code runs and we're done with the object, and currently that's our top right there. Let's say we're done with the object, and so we no longer reference it. But notice an issue here. Even though this very large object is no longer in use by our program, and technically it's not part of the meaningful data structure, it's technically not in the stack. At the implementation level, it's still there. And that means Java cannot garbage collect that memory. So there's sort of a memory leak here. Memory can be used up that you can't reclaim because you haven't properly erased that. So here's an improvement to the pop to deal with that issue. So this is one of those sort of nuances of implementation that I wanted to bring up in this session here. So this one takes a little different approach. It first grabs the object in a variable. So here we were just returning the object. Here we grab the object in a local variable. Now we assign s.top as null. So what would have happened here is we would have wiped that out, and we would have had this O is pointing to that very large object during the execution of this. And then we can decrement top down to 3 and return O. And so when we're done with that, of course, after we return out of this procedure, this reference to the object goes away. So when the main program no longer references it either, it can be garbage collect. So that's one of those nuances about implementation of these things. A similar issue will come up in queues, and I won't do that in queues. But and of course, the other issue here is that if you try to push too many elements, here this code here doesn't even check. It's possible to say let's fill this up, throw a bunch of stuff in there, and then at this point here, top is going to be 7, right? And then if you do top is top plus 1, you get 8, and then when you do the assignment in this line here, you get a array overflow error. So that's not part of the a limit on the stack size is not part of the logical definition of the ADT. This is more of an implementation concern, but that also needs to be dealt with in any implementation. One way to do this is to use dynamic arrays that grow, but that's kind of out of our scope right now. So now I want to move on to queues. Okay, a queue, of course, is first in, first out, like getting into the line at the bank or the post office. And this is often useful also in computing for priority kind of situations where you want to prioritize processes to be taken care of. And as you can imagine, of course, well, we can draw it like this. So whoever goes first into the line, if A goes in first, then B, then C, then A should be the first one to get out. Okay, let's take a look at the ADT specification of this. I'll make this a little bit smaller. Very similar to stack, we make a queue object. NQ is like push, DQ is like pop, except the behavior is different in terms of FIFO instead of LIFO. But we also have size is empty, and like top we have front. So the specifications are very similar for some of the details of not being able to DQ or pop an empty queue or stack, but the order in which things come out will differ, LIFO, FIFO. Okay, let's just jump right into the implementation here. Here's the code. Queue will be represented as an array. Let's give them numbers here. Now we need to be able to point not only to the first element in the queue, but also the last. Because think about what happens when, first of all, the first thing that gets queued is obviously going to be written here, and then maybe somebody else lines up behind them, and then somebody lines up behind that. But when we dequeue, we're taking that one out there. So unlike the stack, where all the data is piled up beginning at the beginning of the array, and you only need one pointer to the end of the array, here the beginning of the array is going to march, the beginning of the queue is going to march its way down through the array, as other things are NQ'd and then things are DQ'd, and then it can actually wrap around where the next thing in line is going to be around the corner there, right? So this is D here is the first thing to be DQ'd, H is the next thing to be NQ'd. This is the position to write the next thing into. So to resolve all of this, we need to have both head and tail pointers, and we need to keep track of potential wraparound. So let me clear this thing out again and show you what the head and tail pointers look like. Initially, head is always going to point to the first thing in the queue, and tail is always going to point to the next place to put something. So right now, that's the next place to put something. Here we have a special case. Head is also pointing at the same place. Normally head points at the next thing to a DQ, but there's nothing there. So in the special situation where head is equal to tail, that means it's empty, okay? But then as soon as we NQ something, let's say we want to NQ object A. So object A first gets assigned to the position Q tail, and then we test to see if it's reached the length. If so, we do a wraparound, else we just increment tail. So let me just do that incrementing tail. Tail was 1 and now it's 2, which I'm indicating with an arrow, but this is really position. In fact, maybe I'll change to that right now, just to make clear what the representation is. It's not pointers. Head has a value, tail has a value. Right now, head's value is 1 and tail's value is 2. Okay, so suppose now I want to NQB. Again, assign it where tail says to go, and then we need to increment tail to 3, and so on. So imagine that going on, and maybe eventually tail is let's say 7, and the whole thing is full of up before 7 is full of stuff. And if we've done some DQs, notice here I've written this code differently than the book to solve that problem of garbage collection. I grab the object first, I check to see if I need to wrap around, else I increment, and then I return the object. So say we had done 3 DQs here, we would have actually wiped out the cells before and then return the objects that were in them, and head would now be equal to 4. Okay. Now let's look at the situation here. We want to NQ G. So tail is 7. So let's write G there. But then it says if tail is length, tail is 1. So this is the wraparound situation. So we now set tail to 1. And the next thing that's NQ'd will be now NQ'd here in position 1. So if I NQ H here, I write it there. And then I increment tail to be 2, and so on. So you can see it going around in circles. Of course, we don't have error checking here. There should be error checking if you get too many things in the queue. Tail will catch up to head, and we'll try to write over what was there before. That should be added to this. There's another way to write this with modular arithmetic. I'll just show it to you really briefly here. This is actually going to replace NQ and DQ, so I'll go ahead and just replace them. So in this approach, you can do it with 1-based indexing, but it's most convenient with 0-based indexing. So I'm going to switch this array to 0-base indexing. So this has 7. This is an array of size 7. Length is going to be 7, and I want to NQ an object. So I want to NQ G here, just like we were doing before. So Q tail is X. Okay, tail is let's put G in there. That's an error, by the way. That X is supposed to be an O. I'll fix that in the notes, or maybe I'll just fix it right now. O. Okay, now we just say tail is tail plus 1 mod length. And so this all has worked. Before we had the test, are we at the end? If so, make tail 1. Otherwise, add 1 to tail. This does that all in one statement. So it's just kind of a simpler way to write the statement. So tail is tail plus 1 mod length. So 6 plus 1 is 7. And so that gives us 7 mod 7. Mod is the remainder after division. 7 divided by 7, remainder 0. So that automatically makes tail be 0 without having to actually test. And then the next time, if you say tail is tail plus 1 mod length, 0 plus 1 is 1. 1 mod 7 is 1. So that's how that works. Okay, lists. Lists let you take a collection of data, a collection of objects, or store them in a sequential manner, a sequentially ordered manner. You could not care. It's possible that you don't care about the order. It's possible that you're just treating it as a set, and the fact that they're in some linear order is not relevant. Or it could be that there is some significance to the ordering. The operations you do on lists can include inserting something in the list, searching for it, finding what comes before and after it in a list. And I'm going to give these operations later on in a more abstract dynamic set ADT that we will also explore other implementations of. Let's kind of jump right now to what's both the implementation and kind of a way of thinking about lists. We often think of lists. This is going to be a singly linked list. They often consist of a data structure called a node, and it might have, say, a key, which is where you store your data, like A or whatever, and then next, which is where you say, here's the next thing in the list. And so we usually draw them like this with C in it, and then often we write a slash through there to indicate nil, or the null value, the end of the list. We need some kind of pointer to the head of the list. So if the list object is called L, usually there's an instance variable L.head, the value of which will be the first cell in this list. So that's a singly linked list. A doubly linked list elaborates on this, where the okay, we got L.head again pointing to something, but now the list nodes have 3 parts. There's the key and the next, but we're also going to have a prev right there. And so just like the next of the end of the list was nil, the prev of the beginning of the list is nil. So this will point to the next thing in the list. There's B, this points to the next thing in the list, just like above. There's C, but then these point back. Okay, so the advantage of that is when you're somewhere in the list, if you want to know what's the element previous to C, up here you can't get to it directly. You're going to have to search until you find the element that points to C. So you're going to have to research the list. Whereas here, if you're already at C, you can then go back and get its previous element. So prev operations and doubly linked lists are just as efficient as next op. Or we're actually going to call this predecessor and successor. In the logical entity, what's the successor, what's the predecessor? In the implementation, that's going to be done by following next and prev pointers. So that's a doubly linked list. And there's also these other kinds of lists called, well, there's circular lists where you can say, well, why waste this base here? Why not have the prev of the head point to the end of the list. So you have a fast way of getting the end of the list. In fact, why not have the next of the end of the list point to the beginning of the list? But the problem with that is now we lost a way to tell when we got into the end of the list. And so the way that is handled is, I'm going to have to make some room here, with sentinels. We make a special node, and maybe I'll make that a red node. It's a special node that has no data, but is used to mark the beginning of the list. So L dot, and for some reason they call this L dot nil instead of L dot head, because we're not pointing to the head anymore. We're pointing to essentially this is the nil element, and then this special node here handles that situation. You know, its next points to the beginning of the list. Its prev, instead of this here, will point to the end of the list, and then the beginning of the list will point back to it. So this is a doubly linked circular list with a sentinel. This object here, because this thing here points to it, L.nil points to it, you can always tell when you got to the beginning or end of the list, because this is an element that you have a special pointer to. And then an empty list up here with a singly linked list, an empty list looks like this. L.head is equal to is null. Here an empty list looks like this. L.nil points to the sentinel cell, with nil in there, and it points to itself back to the end, and it points to itself back to the beginning. And so inserting is then a process of disconnecting these things and putting a new cell there. So that's a doubly linked list, circular doubly linked list with sentinels, this thing I just drew here. And let's erase and go look at some code here. So the code for operating on lists. So insertion, this is what you had to write for your homework, except now not arrays but lists. Remember you wrote list search for arrays, where you just start with an index and you increment it. Well, here instead of increment it by adding 1, you do e is e dot next. So of course any given time in a search, this works just as well on singly linked lists as well as doubly linked lists. I'll just draw the singly linked part first. So you start out with, I'm going to start at the head. I'm going to see whether the thing here is what I'm looking for. If it is, I will return it. If not, I will say e gets e dot next. So I assign e the value of that field, which means it points there, and then I repeat. I check to see, is this what I'm looking for? If it is, return it. If not, point it to the next thing. And of course, if you fall off the end of the list without finding what you're looking for, that statement e is e dot next will assign e to what's right there, which is null. So you're going to get e equals null or nil. And that's when you know that you have not found the thing in there. Okay? So that is searching. And the tricky thing with lists, as you probably remember from 211, is insertion and deletion. You just have to keep track of all your pointers and make sure you don't lose the end of things. So if you have, let's say, L.head points to a list, we've got the back pointers here, the prev pointers, and I'm going to use this basic kind of list. And let's say we have A, C, D, and we want to insert element B here. So we want to insert this element E. Notice this implementation, the method assumes that you know about the internal structure of the implementation. So this is the kind of method you'd make private to the class, and then you expose it to the world through a public interface like the dynamic set ADT or some other ADT, because you don't want the client to have to know about these cells. But so suppose we assume that we've already implemented, we've already initialized this cell with the data we want, right? So this is E. E is pointing at that thing. And actually, I was going to try to insert it in here, but actually this insertion code just inserts it at the beginning of the list, and that's what makes it efficient order of 1, because it doesn't try to find the position in the list, it just inserts it there. So it's going to be a little messy because of where I drew it. Maybe I will draw it over here. And E is referencing that. So E.next is head. So in other words, make that point to that is the next. If head is not equal to null, in other words, if that was an empty list, this would have assigned it to null, then head.prev is E. So notice that we have now taken that nil out there, and we're making it point back to here. And we haven't lost track of that element, because we still got something else pointing at it. We haven't lost track of this element, because we got something else pointing at it. So now the head is going to be E. Okay, so now L.head, head's a instance variable, so head here is L.head. Points to the same thing as E. And now E.prev is null. And so then after you return, this is a local variable, so it goes away, you can see that this has the right structure. This thing has been put in front of the list, and you can still traverse down the list and come back. And deletion is kind of the reversal of that, and you can work through that. So that is pretty much it. There is a Sentinel version of the insertion that I just showed you that works when you have the Sentinel element, but I'm not going to explain that now. You can look into it. Okay, I thought I was going to be able to get it all into one screen flow, but that is a little bit too long. So let's call this one screen flow A, stacks, queues, and lists, and the next one I will cover the binary trees and the dynamic set ADT. Thank you.